All right. Welcome, folks. I see folks are starting to log in. So I appreciate you taking some time to spend your lunch hour with us and join us on our Ask Mayfield Anything. This month, I'm really excited talking about our design considerations around energy storage systems, something that we at Mayfield Renewables have been doing a lot of lately. So I have members from our team on this edition, and so going to be going through that. As people are logging in, what we like to say is, this is intended to be very conversational. So amongst the four of us, we're going to be, talking back and forth about all of these topics, but also we want to hear from you. So if you have questions, what we ask is that you put them in the question and answer section of the Zoom link. Using them there, it really helps us make sure that we're keeping track of the questions. So please don't use the chat, use the Q&A section, and then that way we can make sure we get your questions. As we're going along, please send those in. If I can get those questions in real time, we'll do that. Sometimes we might save some for the end of the webinar, but definitely want to be getting those in and having you all interact with us. So please go ahead and do that. So for those of you who may not know about us, Mayfield Renewables, I founded the company in 2007, and we are, focused. We do a lot of engineering work around solar and solar plus storage systems. And I've been doing education ever since I founded the company way back when. And so, these AMAs are definitely part of that. We do code corners as well, where we talk about codes and standards for the industry. So there's a lot of education that we do. We, have our own courses that we, provide as well on our website and do, in-person classes, things like that. We're also, working with product manufacturers on product market fit. So if they have products coming to market, those are things that we're working on as well. And everything really is, I would say, rooted in education around what we're doing, trying to make the expertise accessible. And so that's, really what we're doing, even here today. So like I said, we have 3 of our own team members available for us today. And so go through and do some quick introductions and, kind of give a little bit of background of who they are, what role they are, what they're playing here. So, we have Brian, Greg, and Zach joining us from the Mayfield Renewables team. So Brian, our director of engineering, comes to us with, more than 20 years experience, has, professional engineer, has been in the industry, probably even longer than I have, I think, Brian. And so, yeah, kind of, can you just introduce yourself a little bit, tell folks kind of, where you're at and what it is that your role here at Mayfield is?
Sure. Thanks, Ryan. Yeah, like Ryan mentioned, my name's Brian Bruggeman. I'm the engineering director at Mayfield. I've been in the solar and doing engineering for over 20 years now. Been doing commercial solar and energy storage projects since about 2016 is when I think I did my first one. And since then, we've been doing these types of projects throughout the US, including Alaska and Hawaii and even Central America. Like Ryan mentioned, I'm a licensed professional electrical engineer in several states throughout the US and also a licensed master electrician in Colorado.
Cool. Thanks, Brian. Yeah, and so Brian's bringing his experience in helping our engineering team, making sure that when we're putting this together, and so he's definitely involved in a lot of the projects that we're working on day in and day out. Next up, Greg is senior design engineer with us. Greg's been with the company for a few years now, and Greg is the only other employee that is in Corvallis, Oregon, at this time. So, Greg, yeah, you want to give us a little bit on your background and kind of what it is that you're doing on these energy storage systems on the engineering side?
Yeah, sure. Yeah, as Ryan said, my name is Greg Kamps. I've been with Mayfield, I think, almost exactly 4 years now.
Yeah.
So I'm a senior design engineer, and I've kind of recently been specializing in the resiliency and microgrid part of the company and kind of focusing on doing a lot of those projects. So it's been a lot of fun. There's been a lot of learning. I'm really excited to be working in that field.
Great, thanks. And then last but not least, Zach. Zach has been, with Mayfield for coming up on a year now, I believe it is. And, coming from a background of solar, was over at Solar Oregon, for those of you familiar with that organization, and working as our senior engineering consultant. And so, Zach, as we're going to go through, we'll be talking a lot about our feasibility studies. But yeah, can you give us a little intro as well, Zach?
Yeah. Hey, everybody. I'm Zach Snyder, and I've been pretty deep into microgrid feasibility. Like Brian says, work at my nose a lot of time. A lot of aspects of it, including energy modeling and working on our processes around it. So excited to talk about that.
Great. Very good. So we're going to, kind of dive into this topic. And so design considerations for energy storage systems. So as we're going, we're going to launch a quick poll for you all just to kind of get a sense of who's out there in the audience and kind of what brought you over here to the webinar. And so we'll leave that up for a couple minutes here as we get started, and be able to give you that opportunity to check in with us. So with that, to launch all this, to launch the topic, as probably not a surprise to folks in the audience, energy storage, it's growing. It's growing very, very quickly. We are seeing, a lot of new products come to market. We're seeing a lot of demand for this. And so you can see from this chart is, the growth in the industry with our estimated values there in 24 and 25. And so you can see just how quickly this side of the industry is growing. So the solar plus storage, and this is true across the board in terms of if you're working residential, C&I, or utility scale. And so, this is a big reason why we have embraced this, I would quite honestly, at Mayfield. And so, probably 18 months ago or so, we made a very conscious decision that we were going to focus in on the C&I space, and we are going to really put a lot of our attention to energy storage. And so, Brian has been very instrumental in kind of that movement within our own team. And, I think we've made quite a lot of progress on that. So I think, Brian, you were noting that, a good percentage of our systems now that we're doing, our engineering systems, I should say. So again, our business is kind of split into a few different areas, but our engineering business, we're doing, what were you saying? Was it like nearly half the systems were incorporated?
In 2023, roughly half of the systems that we did the design and engineering for included energy storage. And for 2024, we definitely see that growing. It'll definitely be over half based on what we're seeing and hearing from our clients. And I would add that these are typically systems that are around 100 kilowatts up to around a megawatt of energy storage.
Okay. So yeah, and so that's actually, so I just got back from Intersolar last week down in San Diego, and that was I'm a little bit focused on that side of the business, but that was where I was talking to a number of people around C&I and just kind of the challenges around that. And part of that is, what are the components that are available? And so I think we'll, kind of talk about that a little bit, and just kind of that integration, especially when it gets into the engineering side, the integration of the components. And so definitely we'll touch on that as we go through the discussion today. Okay. So with that, we're going to take this discussion, the way that we framed it and kind of prepared around this is kind of the arc of the project, really. So starting off feasibility studies. And so we're going to have Zach talk about that, and we'll all just kind of, since we're all involved at some level of the feasibility studies, talk about that, but then get into engineering and then into commissioning. So kind of that arc of the project life, if you will. So with that, Zach, I'll let you go ahead and kind of take over here. But talking about feasibility studies, so kind of opening us up with what is a feasibility study, and what is it that we're looking for when we're engaging with clients on doing these.
Yeah, so as you're mentioning, the big growth in battery storage, there's been probably over a shorter period of time, a huge growth in feasibility studies. I don't think there's a whole lot of folks in the space who really specialize in feasibility studies. And there's also a ton of grant opportunities that cover this preliminary aspect. So in terms of what that have come online. So in terms of what a feasibility study is, it's really aimed at taking a look at what are the constraints and honing the client goals and also creating viable solutions. For example, a system architecture for a microgrid. And so obviously there's people use the word feasibility study as well as microgrid differently. Microgrid, we're talking about really anything battery based. Usually that involves PV, oftentimes, sometimes a generator, etc. And the feasibility process, I think, probably varies in terms of how that's done. I can talk a bit about how we do it, but it's really it's something that should be done. I think it's something that should be done in every CNI or community scale or utility scale battery-based system. And it's something that should be done specifically before you arrive at what are the resource sizes. So the battery size, PV size, and I think I can talk about this, one of the key values of a feasibility study, something that's become really obvious to us, is that it's a hugely conversational process with the client. There's a lot of education that can happen during a feasibility study for us as the analysts, but even more so for the end client, often for the developer EPC. And one of the key values is bringing those expectations about what is the system going to do among all parties into alignment. Everybody's got a clear picture, and then we can move forward with the project and make better decisions and also get a more optimal system. So I have a few images, and there's a couple other slides. I'll just touch on this stuff briefly before I walk into how we do feasibilities. But part of our process involves sometimes putting together a synthetic load curve. Sometimes we have the ability to just have a load curve from historical data. So on the top, you can see we use a couple different modeling softwares. One of them is Zendy. And that's just an example of a load curve. You can see different example curves for different months with the different color lines there. And then an example of a tool, we use something like a fluke meter or a megameter sometimes to do a dedicated load study when we need to get interval data that can be really important for the process. That's what you're seeing there.
So on this on that top one, so we're looking at basically all 12 months of the year over the 24 hours in a day and just kind of looking at what that demand is. So we're looking at kilowatts in this case, right? So this is
correct.
What the instantaneous power draw is. So of course, from that we can decipher what the energy usage is. And so this is a major input. Can you speak just a little bit on the synthetic curve versus the, collecting that data? So a synthetic curve, I believe Zendy has, they've some typical profiles, commercial buildings, different types of use cases, and we can use those to estimate a curve based between historical data and what that is. Is that correct?
Yeah, so best case scenario, you'll sometimes be able to have interval data from a past load study, or maybe more commonly just from the utility that has green button data. But if you don't have that, you can take the past energy usage on, say, a monthly scale from utility bills and apply a typical curve. And so there's a couple of different sources of these. Zendy, like you mentioned, has their own representative curves. There's also the National Renewable Energy Laboratory has some for different building types in different climatic zones. And they just represent, it's not going to be exactly what, say you're working with a school. It's not going to be, you pick a representative curve for a school. It's not going to be exactly what a
Sure.
school uses, but it's going to get you into the ballpark, and you can sometimes adjust it based on some rational choices you can make.
Okay, makes sense. Cool.
Yeah, so if we go to the next slide, this is a chart that we walk through. This is a high-level structure of how we structure our work with a feasibility study. And there's 4 sections. The first one is initial data collection. There's a lot of data that we look at, and that includes small things that people are really familiar with collecting, like utility bills. But also it's the client goals, which are really key. That's something I would really stress about feasibility studies in general. We will have something called a purpose analysis or a discovery workshop. And that's more than just, a questionnaire. We've thought about, can we boil this down into a questionnaire? And we've discovered that there's really no like one size fits all list of questions we can ask that's going to give us all the information about the client, how they're going to use the system, what they want out of the system. So we have that kind of conversation. We can do a load study, like I mentioned. That's something that happens on some projects, not on all projects. It can be more or less useful. And sometimes we do a site visit and go and collect a lot of information about the site ourselves, the electrical system, equipment locations, things like that. Then we go into the next phase, which is the technical analysis. And we're taking all that information. And like I said, one of the key things we're doing is identifying constraints. And so these are all sorts of different things that can come up. And in really feasibility studies, one of their great values is identifying things that are hidden from the get-go. So obviously we're looking at code compliance. There may be some codes that apply in some situations, not in others, like for life safety or emergency electrical systems. There might be constraints around, the surge current. Maybe you have a lot of rooftop units that have motors that are driving fans for big HVAC loads, or maybe there's pumps. You have to make sure you size equipment appropriately for that. There's interconnection constraints to do sometimes with the maximum amount of inverter capacity for a net metering situation. And that can vary based on the utility. So that's also, very variable. Sometimes there's no export situations. Oftentimes there's a budget involved. Sometimes that's grant driven. Sometimes it's just these studies are funded out of pocket by the client. But usually there's a budget, and the prospect of a full facility backup or a full community backup is just not there. So we have to be selective with loads. And that can be a really big conversation with load prioritization. And, is load shedding appropriate? How are we going to do that?
Yeah, and that's one I'll just kind of jump in there real quick. So it seems to me like the financial aspect of this, of course, depending on the use case and what's going on. So this might, let's say if it's a resilience project, there's some real financial impacts there, I guess, in the long term. But upfront, there's only so much money a certain entity can be spending on that. And so I guess that's one of the things that I see as being, a big driver on this, I guess, is, we want to back everything up that we possibly can. And I'm presuming that's a response that we get. We have X number of dollars and we want to back everything up that we can. And then it's a little bit of working backwards, I would imagine, working with the clients and kind of back and forth with them on that.
It is. And I would say that budget is often a primary driver. And that's really about, figuring out, we call them feasibility studies. They could be called optimization studies.
Sure.
And it's, because it almost never is the answer, well, no microgrid is feasible. There's something that's feasible, right? So it's the question of what is that? And so I'll touch on this in a second, but there's a conversation aspect of it too. So they see what we can do, and then they're like, oh, well, maybe it's worth spending a little bit more money.
Sure.
That can definitely happen. And so, and one other aspect here, there might be incentives that are driving constraints, but also, your microgrid is not your battery plus your PV plus or a generator. It's those things plus the user, right? Like the user, how they're going to use their system it can really vary. And so some of these that we're doing feasibility studies for are they're going to be emergency shelters, and they've never hosted an emergency shelter event. They don't really know how they're going to use loads. That
Sure.
requires a little bit of imagination, as you can imagine. And also, how are loads going to grow? Are they going to electrify any appliances? Are they going to have electric vehicle chargers? And are they another aspect is, are they going to reinvest in the system? Are they going to add when the battery is towards the end of its lifetime, which will be before the solar? Are you reinvesting in battery capacity? So there's all sorts of So that's this huge field. We're looking through all this data, identifying these constraints. Then we move into the technical analysis proper. There's energy modeling, financial modeling. But we also, and this is one of the great things that we have the privilege to be able to do, is we have such great design engineering resource. We have a designer as part of that process. And actually one of the deliverables, usually, not always, but usually with our microgrid feasibilities, has been a preliminary design. And that's been really key, having multiple people with multiple perspectives in the room through the analysis, because there's just different sources of expertise that come to bear there.
Yeah.
Different considerations.
I'll kind of pop in on that one too, because recently I was working with you, Zach, on a project, and the client came back with, this is what we want. And it was, a way that probably is, it's a method of wiring, I guess, the system up as a whole, just to kind of keep it brief, but that we would rather avoid, quite honestly. But the client is, this is the reality of our situation. This is how our users, that was a great line that you said, microgrids include the users. And so this is how our users are going to be able to interact with this. And so this needs to be part of the microgrid. And so, okay, how can we figure out how to isolate loads properly? How can we manually control loads? And so I think that's a big part of it, making sure that those conversations are being integrated, and then involving the engineers and making sure that, is this even, are we going to triple the cost of this project because of this one component that, we have the special engineer for them. So I think that's a good, the thing you were saying about having all the voices in the room is an important part.
Absolutely. Yeah. So so that's really, it's a really iterative conversational kind of process internally. And then we get to the final two stages. And this is that conversational educational aspect of the feasibility study. The first thing we do is we tie all this up into a report, and this is a preliminary report phase. And we're documenting clearly, here's, what the site is. Here are the assumptions that we're making on the financial side, on the technical side. Here's how we performed our analysis. Here's how we built our synthetic load curves. Is the system architecture that we're suggesting, or maybe there's a few different varieties depending on the scope of the study. And then here are the important considerations. And we put all of this in the report, because then that's boiled down into a deliverable that we send out to the client. The decision-making process with end clients can really vary. Sometimes it's just one decision maker, but oftentimes there's a lot of people involved. And that report then needs to percolate through everybody involved in that executive decision-making process. They all have their imagination, their vision of what a microgrid is going to do for them. For a lot of folks, this is a really new thing. Especially for folks who are the clients, who are not in the industry, right? But it's new for all of us to varying degrees. And so that needs to happen. And sometimes people, they're pleasantly surprised by the study. They think, oh, this is going to give me exactly what I want. I see it, it's concrete. But oftentimes there's these little aspects that they hone in on. Oh, I didn't realize the equipment was going to go there. I didn't realize that, this was going to be, so difficult in terms of the resilience aspect during this time of the year, if we choose these loads. And so then we give them an opportunity to come back and say, here's what we like, here's what we don't like. And then we offer, okay, something you can do is reprioritize your load list. And then they get back to us, we wrap that into a final report. and then deliver it. Even then, I would say the story is not really over. We've gotten a lot of the way through the woods, but there's the opportunity then after that final report is delivered that the client still has that deliverable, and they can use that as the basis to make an informed decision, however they're going to proceed with the engineering of their study. So that's the process. And yeah, if we go to the next slide, final slide, this is just a great graphic. There's a lot of the information is visual. Some of the information is visual, including the load curves, as well as this is a dispatch graph from Zendy. And what you're looking at here is how the system is dispatching over 3 days. And this is on an hourly basis. So each one of these bars on the chart represents an hour. And again, this is in kW. This is the power that of each of the load and of the resources. So the black line that's outlining the bars below, that's the load of the facility over these 3 days. You can see the blue bars are the utility energy. So this, if you look at this is actually a ton of energy that this particular client is importing. And the system that that was suggested in this case was not going to, offset the majority of their energy. But you can see the yellow bars are the solar, and the green bars are when the battery is dispatching into the system. And this pink line here, this magenta line, is the state of charge of the battery. So it's a very information-rich chart. It allows us to learn a lot about how the system is dispatching and gain insight from that and make key decisions based on that. So there's a few different ways that we present information like this, but in this particular case, you can see these blue bars with the energy being imported are all the same height. And that's because the dispatch strategy for this is really about peak shaving. So the solar is offsetting some energy, and where the solar is not offsetting all the energy to shave down those demand peaks to keep those utility demand charges lower, the battery is going to be dispatching in those green bars, and that's going to allow for that economic benefit. So
yeah, and so I think and first off, I apologize if people picked up on my emergency notification there. Great timing. On this, I think this kind of addresses one of the questions that got asked about. So Marcos was asking how to determine the real relation between PV modules and the energy storage system. And so I think this is part of it, of understanding what is the PV able to produce, and what is that use case as well. So if the strategy is all about demand charge reduction, then we keeping those blue lines at a nice level is the important part. But then looking at the real data, what is the expected output? And so using these models, using these Zendy or Homer Grid is another one that we've used in the past, but I know Zendy is, I think, the kind of our main go-to at this point. Using those models is what helps identify what those the PV and the battery sizes, how we're going to relate those.
Yeah, and Zach, you've been mentioning Zendy a few times. Can you talk about what Zendy is and how we use that to model these systems? And
Sure. Yeah, Zendy is one of there's also Homer Grid. There's software solutions, great software solutions provided by companies that they are the main energy modeling and financial modeling that we perform. And so it's kind of the engine. So there's the huge data intake process, and we're making a lot of decisions outside of the model. The model is really something that does the math, right? And does it really quick, and then provides a lot of resources, charts and things like that to be able to understand. And then we take that and we interpret it, and it helps to inform our strategy and our design for the feasibility study.
And then I just got another question that came in. So William asked, when we say 100 kW of storage, he's asking for a little clarification. Is that 100 kW or for 4 hours, meaning 400 kilowatt hour? And so I think the answer for that one would be, the kW being the inverter. Sometimes it's the solar. So it's I would say it got to be clear on what we're talking about. Sometimes we're talking about the size of the PV system, but then we also need to say the battery inverter, maybe it's, has a limitation 100 kW, 150 kW or something like that. And then also give on top of that the kilowatt hours. And so typically, I think very often when we start talking with folks, we start talking about just the kilowatt hours is really dependent on what the model tells us and how much energy do we actually need for whatever that use case is. And so, it's not always going to be a 2 or 4 hour battery or something like that.
Yeah, it definitely varies a lot depending on the needs.
Cool. Well, great. And this, I really like this graph in the sense that, it's helping show, all of these, a number of things all at the same time, and helping people get a good understanding of that. So, with that, a lot of this gets into, the engineering side of it as well. And so that's where we're going to jump into next. And there's definitely a lot of communication, as Zach mentioned, between engineering and the feasibility side. But, when it comes down to doing the engineering and the design, we'll kind of talk about that. And that's where, I'm going to bring Greg in to kind of drive this discussion and kind of talk about what are those big things that we're looking at, Greg?
Yeah. So yeah, basically, I'm going to kind of boil this down into kind of some of the big things we need to think about during the design. This isn't going to be like how to design, but more of the big things you need to think about as you're moving through the process of designing the system. And so, yeah, basically the process is after we have a feasibility study that's fairly well figured out and the client has agreed that this is kind of how they want to move forward. Then we move forward with the design and kind of figuring out more about the nuts and bolts of the system architecture, about the components that have been selected, and how exactly this is going to fit into the existing system as far as the interconnection. And then so moving down this list, we have big things like utility requirements can definitely drive the system architecture, how it interacts with the existing system and how it interacts with the utility. Some utilities have really great understanding and knowledge of what they want and how they want it, and some don't. Some of them, there's going to be more of a learning process as you go through the process. So it's always a great idea to get a utility interconnection application going as early as you can. And it can be pretty vague. I mean, there can be, a fairly small, basically just a site plan and a single line drawing with, no solar stringing and not a lot of detail on it, just enough to get them a picture in front of them, kind of seeing what you're trying to do and, having them be able to comment on, big things that they're going to require as far as like how it interacts with their grid, how, whether what you're suggesting of doing will satisfy the requirements or not. So sometimes it's really clear, sometimes it's not, but either way, get that process started really early, get it in front of them. And then sometimes there's comments that come back and, that's again, an iterative process that you work through with them. And one of those things is grid isolation. So there's a few different ways to isolate from the grid. One of them would be using an automatic transfer switch. A lot of times with these systems that we've been working on lately, we aren't using the automatic transfer switches just because they're kind of always interacting with the grid, with the battery and the solar. There's backfeeding. There's different reasons that it always wants to interact with the grid, that we want it to interact with the grid. So it's not an either or type thing. And so typically what we have been using a lot of is like a grid isolation, either contactor or like a motorized breaker or something like that, that when the grid goes away, it isolates and cuts off the grid so that there's no interaction anymore. And so that's one of the things that the utility cares a lot about. And they want to make sure that what you're using, what you're proposing to use satisfies their requirements. A lot of what we're using is like an SEL relay with appropriately sized contactor or a motorized breaker, as I said. Few different reasons to use one over the other, but it's highly, it relates to the existing equipment, how everything's going to be interconnected to that equipment. what the goals are, what the backup goals are, and there's a lot into it, but those are kind of a couple different ways to do the grid isolation. Another big aspect of these systems is the controls. So the control systems, a lot of times they're built into the BES system or part of it. Sometimes there's a control system built into that, and then there's also like supplemental controls off to the side doing specialty things that maybe the BES controller is not designed to do. But it basically gathers a lot of different information from different points in the system, like from CTs on maybe the solar production, CTs on the panels and what the loads are, CTs on the generator, CTs on all the different assets, and basically uses that information to make decisions, to try and control the system in a way to keep the battery state of charge in a good point and making sure it's interacting with the other systems in the building effectively. So let's see, we have interconnection into the electrical system, which I've kind of talked a lot about. Mm-hmm. And this is a very big part of it. What's existing on the site and how it's going to, like what the goals are, what you're trying to back up, how it's going to interconnect into the existing electrical equipment, the age of the electrical equipment. You may need to, you're trying to keep from change, you're trying to change as little as possible with the existing equipment, but have it interact and interconnect in an effective way and do what you're trying to do. So that's kind of the goals there. Another thing to do early on is reach out to the BES manufacturer and kind of figure out exactly, assuming that you're getting like a kind of all-in-one system, which a lot of these manufacturers are kind of going towards, is like a box with batteries and a battery inverter and maybe HVAC and fire suppression and everything built into a box that gets delivered, set on a pad, and then you just kind of connect the ins and the outs. But you really want to reach out to them early, especially if you're not very familiar about that specific system, and figure out what is included specifically and what is not included, and request their manual, or request ideally like a single line drawing. A lot of times they're a little tight-lipped on exactly how things in their box work, but the more information you have, the more information you can use to design your system. Maybe it doesn't include a disconnect and you need to add one on the outside. Stuff like that kind of gets hashed out there. Reaching out to them too about having a meeting early on to kind of go through what your goals are, how their system works, sharing information back and forth with single lines, and making sure that they they may have comments for the way that you're doing things. They have a lot more information about how their system works than you do. So very important to figure that out. Another thing that can come out of that is whether or not an isolation transformer is going to be required, and what type of isolation transformer, if it is required. There's a lot of different specific types of transformers that they may specify. Maybe it's not needed. I'm seeing a lot of times that it is, though. And if it is, there's a lot of different types that they could want to see. So that's a conversation to have. It's a long lead time item. It's something to figure out early in your system, or it can delay it later. So
right. And it seems like we're seeing that a lot on our systems, just in terms of, and so different manufacturers having kind of some different requirements around what that isolation is, and so understanding that sometimes they just need it to be, they need to have that physical isolation. Sometimes it might be a change in voltage or something like that. And we do have a single line we're going to show here in a minute. Yeah. I was curious, something you said, Greg, about, and this was a question that came up when I was after the show that I was just at. And so you mentioned talking, about systems that are all in one box, they're a complete system. And so I think one of the questions is kind of what that, if we're seeing any sort of trends, and I know that there's a lot of new products on the market. I know things change rapidly, but I guess just within our own experiences, are we seeing that being kind of the go-to solution versus a battery manufacturer paired up with a electronic, the different piece of electronics, and making that system work that way versus an all-inclusive type system?
Yeah, I think more and more it depends on the size of the system too, kind of what different what options are out there and what types of systems are out there for that solution. You know, there's kind of the smaller end of the commercial system, which is, you know, maybe for like a clinic or something smaller, that would be an all like a lot of times it's a all put in a box, or, you know, outside the building, typically on a pad, is what we're seeing a lot of. And then, you know, if it's a much larger system, we've done projects where we're kind of backing up or tying into an existing like system with generators, like a village, like basically a whole village that we're tying into and trying to reduce their diesel generator runtime. So and that would be a much larger system, maybe in containers, but again, still a kind of an all-in-one system. It's kind of leaning that direction, which I think is good.
Okay. Great.
Yeah, that's definitely what I'm seeing too. That I think it is going to move towards more prepackaged systems and standardized sizing to help speed up some of that upfront feasibility time that Zach was talking about.
Yeah.
Yeah.
And I would expect that there's some listing, you know, around 9540, 9540A testing, you know, that's going to be on the energy storage side. But if the 9540 listing includes all the electronics, it's just going to grease out a little bit better. I would expect on both design, engineering, and permitting.
Yeah, absolutely. And that's another thing to try and figure out early and reach out to the manufacturer about and request that information. And a lot of times there's a report accompanying it that breaks it all down and explains what you're looking at for you to understand, because it'll define, you know, setbacks and locations that the batteries and things can go. And that report will also, maybe more importantly, help describe it for the jurisdiction, so that they, who are not people that are professionals, you know, looking at knowing all these codes on a day-to-day basis, it helps break it down for them, so they know how to feel comfortable about it and what to request. So
Sure.
yeah. Yeah, and I guess just to kind of finish going down the list, equipment locations, and I mean, this can be, you know, dictated by, you know, code, maybe the NEC requirements or utility requirements for disconnects, where the batteries can be based on the fire code, the IFC. So yeah, there's a lot to think about there, where everything's going to go, where you're going to put these different pieces of equipment. And then, yeah, just kind of going through all of the different iterations and different codes, and making sure that you're satisfying the requirements of the NEC, the fire code, and the utility requirements as you move through the process of the design.
Yeah, and I know that we've done this, you know, we're doing some preliminary designs, and even the outputs of the preliminary design will impact what that feasibility study is. So it's very iterative. It very much, you know, we're kind of continually going back and forth, and it's, I think, as Zach said, it's, I don't know if the story is ever really fully done, but it's, you know, trying to get to that point of a system that meets the requirements of whatever the clients, whatever those happen to be.
Yeah.
And before we move on, there was a question about NEC, and I just can't help myself whenever a code question comes up. So somebody, Haley did ask about 702.4, 2023, and 702.4 specifically. So for those of you not familiar, 702 is optional standby systems in the National Electrical Code. And so Article 702 is going to come into play for our systems. And 702.4 talks about the ability, essentially it's the ability for the backup system to power whatever loads that we're backing up. And so there's a couple different ways that 2023, there is some language change, and, you know, we can do a manual transfer. We can do a manual connection from utility over to the backup system. And as we described, that's something that we're doing in some of our systems because of the way that the load shedding, exactly what 702 is addressing, is happening. The loads, that some of the loads that are on these panels that are getting backed up are too much for what the energy storage system can do. So if we provide a manual method, they can manually turn everything off or choose which loads to turn on and then switch over. So that's one way to meet it. And then there's a couple of others, and this is probably the more common and the more desirable way, I would say, of doing it automatic. And so making sure that your energy storage system can indeed meet whatever loads are automatically connected. That's a requirement in code. or you can use energy management systems, which are becoming more and more available and more popular, that you can integrate into that as well, so that this energy management system is making sure that the loads connected don't overload the battery system, overload the backup system is what we're doing there. So yeah, so those are, some of those methods that we're doing.
Yeah, and along with that, like you're talking about the different types of loads in 702, that we need to have a good understanding of these loads to verify that they are NEC 702 or optional loads, and they don't fall under either emergency or legally required loads,
Right.
which have much more strict requirements in the NEC. So another thing to keep in mind when you're defining these loads or talking to the AHJ, know if they're actually optional loads, or if a lot of people talked about emergency panel boards, you don't want to put that on drawings because that has significant code requirements.
Yeah, absolutely. And that's something that, we talk about, and this is hopefully early in even the feasibility is part of it, of understanding, are they legally required? Are they true emergency loads, life safety loads? And so there are higher requirements around those. And so identifying those as early as possible, definitely don't want to, show up on the day of installation and then find out that those are, emergency loads. That would be a situation that, fixing that is going to be more difficult.
Yep. Great. Yeah, if we could switch to the next slide, and it's kind of a rough depiction of a somewhat typical microgrid system. This one happens to be AC coupled, which is kind of, I would say, the most common, typically, unless there's a good reason to be DC coupled. There's just more options, I think, available for AC coupled. I think a lot of times it's easier to design around with AC coupled these days. So yeah, going through some of the components, if you're just kind of walking through it, you have the inverters over there. There's obviously modules coming into the inverters, and then they all tie together in a recombiner panel board. There's much more that is not being shown there, but that comes in as an AC being added into everything being combined, in this case, in the main switchboard. It goes through a PV disconnect and a grid isolation contactor before it gets to the main switchboard, but it's coming into the main switchboard as a breaker. And then right next to that breaker, you have the other breaker coming in from the BES system. And like I said, with the PV2, that has its own separate disconnect there. And then this one has an isolation transformer, and that's why it's 480 delta to 480 Y. There's no change in voltage. It's strictly there for isolation. And Brian, I don't know if we want to get into kind of why an isolation transformer or why not. It's kind of a big topic, but
Yeah, it's kind of a long topic. That short answer is that some of the energy storage systems can produce a voltage that can damage electronics, so that needs to be filtered out before it gets to the electric grid. That's why these isolation transformers are there. Yeah. There's several other reasons they could be included. When you're doing resiliency projects, some energy storage systems don't include a neutral, so we need to add a transformer to have the neutral to feed single phase loads, or have the transformer if we need to change in voltage. But in this case, it's 480 to 480, and this transformer was included for the neutral to feed single phase loads.
Yep, that makes sense. Okay, yeah. So then I guess also this system has a generator included, and again, everything's coming together in that main service panel. It wouldn't have to. Sometimes there's a separate panel board and then one breaker tying into the panel that's being backed up. This one, and we're just using this main switchboard to bring everything together. And then down on the lower right too, just to kind of talk about what that is a little bit, the controls and some of the other systems that are part of the BES need to run on 208. So there's another separate feeder there to feed those loads. So there's a 480 to 208 transformer there, and a little disconnect for those loads in the BES. So
yeah, that's often for HVAC units is one of the
Okay.
more common things we need to power an auxiliary transformer.
So yes, I think as you know, we're looking at this, there's multiple ways to go about it. In this case, we're using motorized breakers and a microgrid controller to do that isolation from the grid or connection to the grid, as the case may be. And so, you know, sometimes we'll actually see contactors. Sometimes if it's a small enough system, might be integrated. So that microgrid interconnect device might be integrated with the power electronics. And so, you know, this is just one of, you know, probably lots of ways that we can do this. Just, yeah, kind of wanting to show that to folks.
Mhm. Yep.
Yeah, this was a pretty large project. I believe that main was either 2,000 or 4,000 amps.
Okay.
So doing a motorized breaker on that made sense, where a contactor at that scale didn't. I would say
Sure.
ASCO just came out with the first grid isolation device, off-the-shelf grid isolation device. And I think that currently goes up to 600 amps at 480 volts.
Okay.
They're gonna be coming out with additional sizes.
Yeah, that's great.
Great. Okay, so I'm gonna keep us moving on. I know that, you know, this is, as we all noted, as we were preparing for this, we knew that we would have lots to say about lots of different parts, but we'll move, we'll keep moving. We're getting close to the top of the hour. So, you know, commissioning is, you know, also a big part of this. And so Brian I wanted to have you talk a little bit about that. And then, you know, we do have a number of questions. I'm going to see if I can get to those as well. But Brian, if you want to spend a couple minutes here.
Sure. Yeah, and commissioning is required by the International Fire Code. And that a commissioning plan per IFC 1207 is required to be submitted with the as part of the permit submittal. So it's something that needs to be thought of right away as you're putting together the drawings on who's going to be doing the commissioning and how that process is going to look. The system needs to be documented on what the owner's requirements are. That needs to be part of the commissioning. So that would be the feasibility study. Would need to be included with that. Needs to be determined who's responsible for the different areas of the commissioning. Oftentimes the manufacturer will do some parts of it. The controls vendor will definitely do some parts of it. And the engineering team could do parts of it. The utility will also want to come out and most likely do a witness test at this point to make sure the system operates as it was designed and interconnects and disconnects from their grid appropriately. And also during this commissioning phase, there'll be a lot of testing and tuning of the controls to verify that the energy storage and the generator and the solar, all that works together correctly. The solar inverters are able to be curtailed properly and everything disconnects properly. And then there also needs to be training and documentation left with who's ever operating and maintaining the system. So that all needs to be done too during the commissioning phase. Definitely the more challenging part of the commissioning is the controls, making sure all that works properly. And so that there's no finger pointing at the end.
Yeah, and I'd also point out, you mentioned IFC, the 1207 requirement. It's also part of National Electrical Code now in 706. So if you're using a 9540 system and this shows up, it basically says you have to commission it. And then it points to NFPA 855, which 855 has a very, very detailed list of exact requirements on what that commissioning looks like. So that's probably your best, I would think, resource on when you say, well, what do I need to do for commissioning? That would be the place to go. All right. So let's kind of look at some key takeaways here. So, you know, we've talked about a number of things here. And like I mentioned, there are some great questions here. I'm not sure we're going to be able to get to, I'm fairly certain we won't get to all of these questions. There are a few questions, though, that kind of came around consulting and kind of, you know, upfront, you know, how to get things, I guess, paid for, things like that. And so, you know, for us, the feasibility study, which, you know, as Zach said, you know, could be called an optimization study as well. So feasibility, just trying to understand based on the client's needs, what's going to work for that. That is a service that is basically, it's an engineering service that gets paid for upfront. And so, depending on the exact methodology, Zach mentioned, there's grant programs out there for specific resiliency type programs. Otherwise, it's, if you're far enough along in the sales process where, the customer can see the benefit of putting storage in with it, if it's maybe a demand response thing, getting rolled into the overall engineering design. So there's definitely opportunities on the front end where it should be, getting included in the cost and basically having, ultimately the client typically paying for those services. And so one of the questions, I'm going to kind of throw this over to you, Zach, including financial modeling. So the question is, do you include financial modeling with the studies and then payback with energy storage versus just PV systems? So one of the reasons why we have chosen Zindi, there's multiple reasons, but one of the aspects of Zindi is that financial analysis of it. So Zach, I guess, could you speak a little bit to that and just kind of what the outputs of that are, and so how that can kind of help guide those conversations?
Yeah, financial modeling is something that we have done on all of our feasibilities. It's been important, I would say, to the client most of the time. Sometimes for grant-funded projects, they know that they're going to have the money up front, but they still are interested in the financials. In terms of the output, there's different metrics that Zendi provides and that we can calculate if necessary, including the cumulative discounted savings. Sometimes they're just interested in the first year energy savings. Sometimes it's the net present value or the internal rate of return. So there's definitely a conversation about what is important. Those things are more or less important to different clients, and so the financial modeling also, you need to take into account the length of the study and the expected lifetime of the resources. So if the battery is going to drop off at year 10 or 15, which there are some key assumptions you need to make, and so because that's not firmly established necessarily, some of that in the industry. And so so a lot of it is making sure you have your assumptions correct, and then making sure that you're giving folks the right output that they need.
Great. Yeah, and so the financial aspect of it is a major driving force, and so including that analysis is really important. Alvin makes a good point, a good question, about, and we're running low on time. So the set points in inverter set points and the utility requirements. And so I think that's something that, Zach and Greg were both talking about in that feasibility analysis, understanding what are those requirements, what are, can you sell battery power back to the grid? Can you only charge from the grid? Can you only charge from PV? So there's a lot of set points if the system is there as a grid support feature. So we're seeing a lot of systems now being put in by utilities as grid support. So understanding what exactly those set points are, definitely a conversation that needs to be happening with the utility on the front end. And then there's hopefully it's a relatively easy one. Percentage of systems AC coupled versus DC coupled. Greg, I know you threw out, most of ours are AC coupled. Are you seeing any trends, size being a factor for going DC coupled versus AC coupled or anything like that?
No, I mean, I can only speak to, the designs that we've done, not necessarily the industry as a whole, but I would say the lion's share are AC coupled. There might be a specific reason to go DC coupled. Maybe it's a single phase service you're trying to back up and there's just not good options out there. So you might have, be forced maybe to go DC coupled, something like that. Otherwise, I would say most or all are AC coupled at this point.
Okay.
So
cool. Well, there's a number of other questions. We'll keep these recorded and be able to, get back with people directly. And, if your question was still outstanding and want to talk to us about it, here's all of our contact info. Happy to talk with folks. As we expected, there's a lot of really good engagement, a lot of good questions here. So we'd love to keep that conversation going. And of course, you can reach out to us, any of us here, directly via our emails or, phone number or general email as well. And then last couple things, as I mentioned, we are doing our own courses. There were some comments in early on about the 855 and UL 9540. We actually have multiple courses on storage and different codes. Have a couple of 3-hour courses, so get really in depth on those. I encourage people to take a look at those on our website. Really excited about having these available to people. And then, in the upcoming, we're, coming up on RE Plus Northeast, for example, NABCEP continuing ed conference. We'll be at both of those doing some trainings as well. So look forward to seeing people out there. And then finally, just, put on your calendar, hopefully, save the date, next month, February 21st at noon Pacific, we're going to be talking about some racking considerations, looking at some of the changes in codes and standards around that and how those will impact your system designs. So with that, I really appreciate everybody, taking your time to spend with us. Thank you to Brian, Zach, and Greg from our team interacting with you all, and really appreciate it, and hope to see you at on the next Ask Mayfield Anything.
Yeah, thank you.
Yep,
Thanks,
thanks.
everybody.